We say that a square matrix is elementary if we can get it from doing only one elementary row operation on an identity matrix. So as an example, we might take this 2 by 2 identity matrix, and let's say we do the operation row 2 plus 3 row 1. And after doing that operation, we're going to get 1, 0 inside of row 1, and we're going to get 3, 1 inside of row 2. Because we've only done one elementary row operation on an identity matrix, we say that this matrix on the right is elementary. Elementary matrices can be broken into 3 different groups. One group for each type of elementary row operation. If we can form an elementary matrix by multiplying one row of the identity matrix by a non-zero number, I'm going to call that a type 1 elementary matrix. If we get an elementary matrix by adding a multiple of one row of the identity matrix to another row, I'm going to call that a type 2 elementary matrix. And finally, if we switch 2 rows of the identity matrix to get our elementary matrix, we'll call that type 3. Let's go ahead and take a look at some examples of the 3 different types of elementary matrices that we might get. First, what I'm going to do is take this 3 by 3 identity matrix, and I'm going to take row 1 and multiply it by 1/2. When I do that multiplication, I end up with a new matrix that looks like this. And this matrix is an elementary matrix, and specifically it's a type 1 elementary matrix. It's type 1 because it comes from performing a multiplication of a non-zero number on one row of our identity matrix. Next, let's take a look at a type 2 elementary matrix. These ones are formed by doing an addition or subtraction of 2 rows of an identity matrix. Now before we go any further, I do want you to know that I'm picking our identity matrices to be random sizes, and all of the operations I'm doing are also completely random. The idea here is just to give you some examples that you can relate to the definition. Later, when we're actually working on some questions, you're going to know which operations to use, or you're going to be given the elementary matrices to work with already. So back to it. When we do the operation row 1 minus 2 row 2's, we're going to get the following matrix. And this matrix is an elementary matrix, and it's a type 2 elementary matrix. And last but not least, we'll take a look at a type 3 elementary matrix. Here I have a 4 by 4 identity matrix, and we're going to do the operation row 3 switched with row 4. When we switch row 3 and row 4, we're going to end up with the following matrix. And we say that this one is a type 3 elementary matrix. Next, we get to answer the big question. And the big question is, why in the world do we care about elementary matrices? And it really comes down to this theorem. Any elementary row operation we do on a matrix A can actually be represented by a left-sided multiplication E times A, where E is an elementary matrix. I want to give you an example of what this theorem means. So let's take a matrix A, 1, 2, 1, 2, 0, minus 1, and we're going to do the operation row 2 minus 2 row 1. Maybe we would like to get A into reduced row echelon form, for example. After we do this operation, we end up with this matrix. Now, what we want to show is we want to show that we can take matrix A, we can multiply it by an elementary matrix, and we get this matrix down here. Now you might ask, how in the world could we find this elementary matrix that we need to multiply by? Well, the answer is right here in front of our noses. So I'm going to clear this away, and I'm going to create the elementary matrix row 2 minus 2 row 1's. So let's go ahead and create what we think E should be. We'll take a 2 by 2 identity, and we'll do the operation row 2 minus 2 row 1s. The same operation we did to matrix A. And this is going to give us our candidate for E. Alright, remember this one. We're going to come back to this one on the next slide. So our last step here is just to do some simple matrix multiplication. We're going to take our elementary matrix that we formed, and we're going to multiply on the left of matrix A. So I'm going to go ahead and do the multiplication. I'm going to get 1, 2, 1 for the first row of the matrix E times A. Remember, we have to take the entire row times the entire columns here to get those values. Next, I'll go ahead and I'll fill in the second row of E times A. Now I want you to take a look at this matrix here. Does this one look familiar? Have we seen this one somewhere else before? Yeah, this is the same one that we had earlier when we applied the operation row 2 minus 2 row 1s on the matrix A. So this is what the theorem is trying to say. We could either take A and do an elementary row operation to get a new matrix, or we could represent the elementary row operation as multiplication on the left by some elementary matrix. All right, my little epsilons, stay positive.